This is Finite Math, Section 8.1, Basic Elements of Scheduling. Yesterday, we talked about digraphs. A digraph is a directional graph, and we talked about things like in degree, out degree, incident to, incident from, adjacent. We also talked about how to travel along the edges of a digraph and moving in the direction of the arrows. The other element of this chapter is something called scheduling, and we're going to be using a digraph to help us solve scheduling problems. So in order to deal with scheduling, you have to know a couple of vocab words. So in your notes, let's start with processor. A processor is the worker. This is whomever or whatever is working on a task. So for example, if we're going to talk about a processor, we normally say P1, P2, P3, etc. These could be actual workers like plumbers and painters and carpenters. Or if you are in a factory, maybe they represent machines or computers. But it's whoever is accomplishing the task. And that's what our next word is, task. The task is the actual work being done. So the things you need to do, those are tasks, and you are going to complete them with a processor. A task is an indivisible unit of time. And this work cannot be broken up into smaller units. It's always carried out by a single processor. We use capital letters to talk about these, so A, B, C, etc. Or sometimes we're more specific, like PL represents the plumbing job, or EP represents the exterior painting work. But the idea of it being done by one processor is for this chapter. In reality, you might have the painting job in a house being done by 2 or 3 different people, or 2 or 3 different workers. But we're going to consider it as one task, the painting job. And instead of thinking of it as several different workers, we may think of it as the painting crew. When we're dealing with tasks, there are several words that we use to talk about them. If you have a task that cannot be started yet, it is ineligible. So for example, before you can paint the walls, you need to build the walls. So until the walls have been built, painting the walls would be an ineligible task. It wouldn't be ready to do. A task that can be started now is a ready task. When we are currently carrying out a task or working on it, we usually say that the task is in execution. And a task that is done is completed. So these are the words that go with scheduling. When I'm talking about my list of tasks, I may ask questions like, which tasks are ready? Which tasks are currently in execution? Which are our completed tasks? Which tasks are ineligible? Another concern about a task is how long it actually takes you to do the task. That's called the processing time. Processing time is the amount of time it takes to be completed by one processor. And we're going to assume robotic behavior, or humans that are very standardized for the sake of our class. In reality, this isn't true. For example, if I was going to mow the grass at my house, it takes me a lot longer to mow the grass than it does my husband to mow the grass because I am a wimp. So it takes longer. I have a lot of complaining I need to do in the meantime. But we're going to assume that mowing the grass takes a certain amount of time, no matter who is doing it. The notation we use is the capital letter that represents the task, followed by a parenthesis with a number in it. And basically it says it takes Y amount of time for one processor to complete task X. For example, W15 might say it takes 15 minutes to wash the windows. Precedence relationships are another thing we need to consider. A situation where one or more tasks must be completed before another task is ready. So for example, if we go back to the idea of a house, a precedence relationship would be that you need to build the walls, or you need to put the drywall up, before you can paint the walls. Or you need to lay the foundation before you can frame the house. Okay, these are things that are precedence relationships. The first thing has to be done before the second thing can begin. Independent tasks would be any tasks that don't have precedence relationships between them, or there's no connection. So for example, maybe we need to wash the dishes and we need to mow the grass. There's no reason why we couldn't do one before the other, or even if we had two processors or two workers, one could be washing dishes while one is mowing the grass. These could be done at the same time. So this gets to how are we going to take these ideas of a processor and precedence relationships and tasks and turn them into a digraph, something that we can use that'll be useful. And we're going to use this with arrows. Okay, so I have my vertex. The vertex of in my graph, these are going to represent my tasks. And the arrow in between represents the precedence relationship. So if I have an arrow going between X and Y, it translates to X must be complete before Y is ready. All right, so if X must be complete before Y is ready, then that's what that arrow means. I have to be completely done working on X before I can move on in the direction of the arrow to Y. Independent tasks won't have any arrows between them. And you might have some tasks where precedence is implied. So for example, there's not an arrow that goes straight from X to Z. But if X has to be done before Y and Y has to be done before Z, it's implied here that X has to be done before Z. Okay, we are implied that that has to happen right there. So even though X and Y aren't directly connected, they aren't independent because of this implied transitivity here. Okay, so in this chapter, we're going to be using project digraphs to help us with optimizing schedule problems. Okay, so a project digraph is going to represent a bunch of tasks. So it is a digraph that shows all of your tasks in a project. So here is, there are several tasks here. I have showering, dressing, drying hair, fixing hair, eating breakfast, brushing teeth, etc. Okay. If I was going to talk about this, the number of tasks in here, it looks like we have 1, 2, 3, 4, 5, 6, 7, 8 because we have this start and we have this end. But these start and end are just imaginary tasks. They aren't actual things that need to get done. Notice that they have a time of 0. The start and end are made-up tasks just to give ourselves some grounding, to give a definite location, to tell the person who's working on the project, here is where you start. And once you get to the end, you're done. So these don't really count. So the number of tasks would be the number of vertices that I have, except for start and end. So shower, 1. Dress, 2. Dry hair, 3. Fix hair, 4. Eat breakfast, 5. Brush teeth, 6. The other thing that we see are precedence relationships. The precedence relationships are going to be your arrows. Precedence relationships will tell us something that needs to be completed before the other thing begins. So for example, you need to shower before you dress. This is important. If you try to dress first and then go take a shower, you are going to have wet clothing. Not a good idea. Other things would be like eat breakfast before you brush your teeth. Okay, so this is not something that you want to do at the same time. You don't want to be currently eating and brushing your teeth simultaneously. That's not a good plan. Okay, so what we want to do is completely finish the first thing before we start the second thing. So the fact that shower comes before dressing is important because you don't want to start putting on your socks if you're still in the shower. Okay, you want to be completely done with that task before you move on. Independent tasks would be tasks that could be done in any order. So for example, we could eat breakfast. And I look at this, and eat breakfast isn't connected at all to showering. So when you get up in the morning, you could shower, you could eat breakfast, you could do the, one before the other, but it doesn't really matter where they go. There's no connection there. So independent tasks, no connection between them. So the idea of a project digraph is it shows all of our tasks. The arrows show the precedence relationships to help us move through the graph in the right order. So it gives us an order for this. All right, so scheduling problem. This is our goal. We are trying to optimize this. And we've been optimizing for the last several chapters. In chapter 5, Euler circuits, we were trying to find an optimal Euler circuit, and we said, you know, if we couldn't get enough vertices put in there, we would add some edges. You know, if we want the optimal Eulerization. In chapter 6, we were looking for the optimal Hamilton circuit by checking using brute force, going through all of the possible Hamilton circuits and trying to find the best one, the cheapest one. In our last chapter, we were looking for minimum spanning trees. We were looking for the smallest way to connect all of the vertices. These are all optimization problems. We're still working on that. So, for example, you wreck your car, and there's 4 repairs. You've got 2 mechanics. So the first thing I notice as I'm looking at this is we have, my pen selected here, we have 4 repairs. There are 4 things that need to be done. That means those are my tasks. There are 4 things that need done. And there are 2 mechanics. So I have 2 processors. And we know that exterior bodywork must be completed before painting and exterior work can begin. Now here are my tasks. Exterior bodywork is going to take 4 hours. We're going to call that task A. Engine repairs, that's task B, 5 hours. Painting and exterior work is 7 hours. And transmission repair is 3 hours. And we know that A has to be done before you can start C. And that makes sense. You got a big old dent in the side of your door. You don't want to paint it before you fix the dent. So fix the dent first, then paint. You also don't want to be doing those things at the same time either. Now, possible schedules. How could we put this together? Oops, there we go. Possible schedules. So here's one where I have my tasks and A, processor 1, so the first worker, he's going to work on A, which takes 4 hours, and then he's going to start working on D. In the meantime, processor 2, the second mechanic, he's going to do task B, and then he is going to pick up with doing task C. Before processor 1 gets done at like 7 hours here, there's nothing else for him to do. So if you don't have anything to work on, we call you an idle processor. You're just sitting around waiting for the next task to come in. From this, it takes up, we can look at this timeline of how long it takes us to do, and we know that we have a finish time of 12 hours. And it feels like we could do a little better. There's a lot of idle time right there. So let's look at the next one. Here, I've got task A. Worked on, and then B, and then processor 2 works on D and C. This time, our finish time is only 10 hours. But then you notice it says illegal schedule. Why is this illegal? And if we were in class, I would have somebody raise their hand and say, why is this schedule illegal? But we're not, so I'm going to tell you. So why is this schedule illegal? When I'm looking at this, I know that A has to be done before you can start C. And that's not what's happening here. Notice the overlap. So essentially what's happening is the one guy's trying to get the dent out of your door, and the guy with the paint comes up and says, hey, I'm ready to start painting. And he's painting on top of the guy working. That doesn't work. We can't have that overlap. In fact, C can't physically start until A is totally done. So C cannot start until hour 4. It's starting right now here at hour 3. So this is an overlap schedule because it violates the precedence relationships. So everybody imagine taking this task C and scooching it over an hour. Okay, that's what this bottom schedule would happen. We take C, we scooch it over. That puts an idle hour here between D and C. But now A and C aren't working at the same time. And we have a finish time of 11 hours, which is still a little bit better than we started. Here's another schedule where I arrange the tasks. Notice that A is totally done before C starts. We still have a little bit of idle. And this one also takes 11 hours. And if I take a highlighter just to double check, A has to be done before C can start. I can see A has to be done before C can start. There's not overlapping. Here, there's that overlap. A has to be done before C can start. A has to be done before C can start. So we want those tasks to be completely done before we start the next one. Now, the other thing that this tells me is due to that precedence relationship, A, which takes 4 hours to do, and C, which takes 7 hours to do, we cannot do any better than 11 hours for this project. There is no way to schedule this project and get it done in less than 7 hours. Even if we have a ton of mechanics working on the job, it takes A, 4 hours to get done, and you cannot start the next 7-hour project until that task is totally finished. So 11 hours is what we call our critical time. every single project has an absolute minimum time. And most of the time it's not 0 or 1 or 2. It's a bigger number than that. So for example, if we are going to build a house, we can't build a house in an hour, no matter how many workers we have. You know, it takes time for the concrete to dry. It takes time for people to frame the house so that you can attach the drywall. Things have to be done in a certain order. Things have to be done before each other, and some things take time to complete. But this is what our goal is for this chapter. We want to take a list of tasks, and we want to try and find the absolute minimum time it would take to get all of those things done. And we're going to use a project digraph to help us out. So how do you make a project digraph? I'm going to show you one that's already done first. So if you turn the page, we have building a dream home on Mars. Now everybody pay very close attention, because I'm going to show you how you would build this. Then we're going to build one together very slowly. And then you guys are going to do some on your own in groups. So here we go. Building a dream home on Mars. You have to earn a trip to Mars, and you have earned, typo, you have earned a trip to Mars and will be living in a Martian habitation unit. The MHU must be assembled by special construction robots that can be rented by the hour. The precedence relationship in the chart must be followed. You have to tell the robots when to do what. How many should you rent, and what's the quickest way to get the job done? So what we're going to do is we start off by listing all of our tasks, assigning letters, and talking about how long they're going to take to do. So here are all of our tasks. We have to assemble the pad, assemble the flooring, etc. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 tasks that need to be done. And we know how much time it takes. So assemble pad, we're going to call that AP, and it takes 7 hours. Assemble flooring, AF, 5 hours, etc. So we have these timings there. Okay, and then we're going to talk about precedent tasks. Precedent tasks come first. Okay, or in other words, they take precedence over the task that is after them. These tasks are more important. So when I look down through here, here's what I see. I see, for example, that AP and AF are precedent over IF. Okay, now I'm going to circle those, and out to the side I'm going to write what that means. That means that AP has to be done before IF, and also that AF has to be done before IF. So precedent tasks come before the actual task. These tasks take precedence over that task. You have to complete the assemble pad and assemble flooring step before you can actually install the floors. So there were 2, but even if you have something like this, here's IC and FW. This is the precedent tasks. That tells us that IC has to be done before you can do FW. So the first thing you want to do when you're working a problem like this is you want to start and ask yourself, I am making a project digraph, so I am going to start with a start. Okay, so you make a vertex for start. And then you say which tasks can be started right away. And the ones you want to look for are the tasks that have no precedence relationships. So I look, there's nothing in front of assemble pad. There's nothing more important than assemble floor. There's nothing more important than assemble the wall units. And there's nothing more important than assemble the dome frame. There's no precedent relationships there. So that means that these tasks are all ready tasks. So when we're looking at our start, AP, AF, AW, and AD could all be started right away. So I would draw an arrow, an arc, and create a vertex for each of those tasks. From there on, I would build one precedence relationship at a time the rest of this picture. So for example, I know that AP has to be done before IF, AP before IF. So I can put a vertex for IF on the graph, and then I can draw an arrow from AP. AF also has to be completed before IF. And you're going to do this one at a time until you get all of the tasks on the graph and all the precedence relationship arrows in place. Here's another one. IC to FW. IC has to be done before FW. Well, there they are in the graph. There's vertex IC, there's vertex FW, and we've drawn this picture. Okay, and you would do this for all of your pictures. Once you get to the end, anything that doesn't have a connection would go to the end of your project digraph. All right, so let's make a smaller one here. It says draw a project digraph for the project consisting of the 6 tasks described by the following table. All right. Now, one thing some people do is they like to put all the vertices on here and just sort of start randomly doing that. Personally, I like to think of it like a flow chart. So the first thing I'm going to do is I'm going to list my precedence relationships. Okay. Because this helps me a lot. So I look and I see A has to be done before C. And I'm going to write that down. A has to be done before C. Also, B has to be done before C. So precedent. B is precedent to C. B is more important than C. C has to be done before D. So I'm going to write that down. C has to be done before D. D has to be done before E. And B has to be done before F. These are my precedence relationships. And basically what this means is that these are the arrows I'm going to have in my graph. These are the edges of my graph. I just have to put them in one picture instead of a list of 5. So I know it's a project digraph. And I didn't mean to cross that out, but unfortunately I did. So I'm going to start with a start. In a project digraph, we start with a start. All right, so here we go. I'm going to put a vertex. I'm going to call it start. And since start is an imaginary task, I'm going to give it a time of 0. The next thing I'm going to do is I'm going to ask myself, which tasks are ready? Ready tasks have no precedent relationships, which means there's nothing in front of them. So in our case, A is ready and B is ready. A is ready and B is ready. So those are my first 2 vertices I'm going to put in my picture. I'm going to arrow over to A, which has a processing time of 2. And I'm going to arrow over to B, which has a processing time of 3. Okay. Right, those are my first 2 tasks. Now I'm going to go one at a time through my precedence relationships and get them put on this picture. So for example, I know that A has to be done before C, so I need an arrow on my graph from A to C. Or you could think A has to be done before C, so I need a vertex for C, and I need an arrow coming from A. Now I'm going to cross that off because I put that on my picture. I also could put the arrow from B to C. I've got that one done as well. A has to be done before C, B has to be done before C. Okay? I notice C has to be done before D, so I need to put vertex D on my graph, and I need an arrow going from C to D. There's that one. The next one I see is D has to be done before E. So if D has to be done before E, that E is 4, and there's that arrow. And then finally, we have B before F. Okay, so F isn't on the picture yet, so I need a vertex for F. F is 8 hours. B has to be done before F. All right. So we're almost done. I've got all of the precedence relationships on there. All of these are done. I have all of my vertices on there. And the only thing I need now to complete this project digraph is to have an end. End is a task of 0. So how do you decide where the end is or what goes to the end? What you want to look at is every vertex should have an out degree. So A goes out to C, B goes out to C and F, C goes out to D, D goes out to E, but E's not going anywhere, so it needs to go to the end. F is not going anywhere either, so it also goes to the end. Okay, so that's the notes that we're going to do today. We're going to pick up with section 8.3 next time. What you're going to do after this, and the substitute's going to help you out with this, is an activity where you are going to build some project digraphs, and you're also going to answer some questions about digraphs like we talked about yesterday with the teams. Okay? All right. So your instructions for the next little project. You are going to work in a team of 2 or 3 people. Okay? in your team of 2 or 3 people, you are going to have one paper. Okay, and the sub is going to give you that one paper. It has 5 questions on it. If you are working in a team of 2 or 3, I expect to see at least everybody's handwriting present. So if there are 5 questions, then maybe you write on every other one. But 2 people, I should see 2 distinct handwritings. 3 people, 3 distinct handwritings. So everybody has to write, although you can work as a team to get the right solution. And that's what I expect you to do, is to work together and not independently. Right? Try to answer each other's question. Try to come up with the best answer possible to the question. Think about it. Argue with each other if you need to, but try to prove that you think that's the right answer as you're working through. Once you get the paper done, you're going to turn it in. Okay? If you and this is due by the end of class. All right, so due at the end of class today. Okay, so that paper is due at the end of class today. The other thing about the paper is that you need to make sure everybody's name gets put on that paper. So one paper for each group. Everybody in the group doesn't need a paper. One for each group, and we'll go from there. Okay? It's important to me that you try these on your own, so don't be stressed out if you think, oh no, this is wrong. Okay? Maybe if you're confused, look over at another group where that is doing it and they feel like they're pretty comfortable and say, hey, can you help our group out? That's collaboration. All right? So a group of 2 or of 3, you can't work in a group of 4. If you work in a group of 4, you need to split yourself into a 2 and 2 group and have 2 pieces of paper. All right? And on the next class, we will work on section 8.3.